We're going to go through the basics of the equations for open channel flow. I'm going to start with what's a kind of a typical looking cross section of a stream. Different streams are different, but often you have a central channel that contains the stream under most conditions, and then about once a year, maybe a couple times a year, the stream will come out of its banks. There'll be a big rainfall and runoff, and it'll come out of its banks, and then they'll spread out on the floodplain. And that dissipates energy, and so it's more area. You can have flow being a lot higher without it rising a lot. And this can vary. Where I am now in central Pennsylvania, the stream I'm on, when it's flooded, comes out of the bankful stage, it doesn't come up that high once it gets up there because there's a pretty wide flood plain. In the Ozarks, where I was before, it had a lot of rocky and narrow gullies, and you'd have a storm and it could come way out of its banks and go up quite a bit high. So it varies quite a bit. So here we're going to do the calculations using the Manning's equation. The Manning's equation is the basic equation we use for open channel flow. And here we have a 35-foot width here, and then the bankful depth is 3 feet. So when it's in its banks, it's right there. And we're going to do the calculations for that. And the dimensions that are given, I'll give you the numbers. I have it on a spreadsheet here. We won't put the details of the geometry calculations and stuff on this sheet. So the Manning's equation, which by the way is for what we call normal flow. Can you read that? And it's for uniform depth. So Manning's equation says that the flow in cubic feet per second equals 1.49 over n, r to the 2/3. What's r? We'll get to that in a second. That's in units of feet. S to the 1/2. S is the slope times the area. Or V equals Q over A. And so we could bring this A over here, and then we only have this part of the equation there. And this area would be in feet squared. Oh, wait a minute. This, I get feet to the 2/3 times feet squared, and that somehow gives me cubic feet per second. Now, this equation violates everything you've learned since 8th grade about canceling units. It's a unit-specific one. In fact, there's one for metric units, cubic meters per second, equals 1.0 over n, r in meters to 2/3, slope a meter squared. So this is a unit-specific equation. Again, it doesn't make sense in terms of units, but it's an empirical equation. And in here on the denominator of this is Manning's, usually we just say Manning's n, Manning's coefficient, or Manning's constant. Maybe I'll say coefficient. And that's a number. So for concrete, we often use 0.013. So something that magnitude. And so it's in the denominator. So a higher number is more friction, and therefore would be lower flow. It's the denominator here. So higher n is lower, more friction, lower flow. R is the hydraulic radius. Which is equal to the area over the wetted perimeter, where A is the cross-sectional area. The wetted perimeter is the perimeter that is wet. I'm going to write that out. So for this cross-section here, we have the area here of that, and then the wetted perimeter is the perimeter of it that's wet. So not the top there, but where there's friction. So that's our equation. S is the slope or the hydraulic gradient that we've used before in groundwater and pipe flow and stuff. For open channel flow, Manning's equation is uniform flow. So if this is the ground surface, and if it's all 2 feet deep, the water surface is 2 feet above the ground surface, so that would be the same slope. So we can think of that as hydraulic gradient. It's also for open channel as the slope of the ground. So we'll start doing our calculations here. I pasted the formulas in here, but I'll just tell you the results of this. So when it's 3 feet deep, we get an area of 112 feet, a wetted perimeter of 42.7 feet, and then this is 112, looks like 1/2, it's 112 feet. So the hydraulic radius, the R, is 2.6 feet. So we'll plug those into our equation when it's 3 feet deep, and Q equals 1.49 over N. What's N? N, I can look up from a table here. I can also find some more detailed guidance on that. For example, I found a table somewhere that had the N's and listed for a different size gravel. For D84 52 millimeters, this table that I found somewhere, not this table, but different table, said N equals 0.030. So it's 1.49 over 0.030. R to the 2/3. That's 2.6. And again, we've always taught you, write your units and cancel units, and doesn't apply to this one. It violates what we've taught you. R to the 2/3. Then the slope is in there somewhere. 0.00015. So it's a fraction. It's 0.00015. And that's to the 1/2 power. And then the area. And again, I could write this as a V and pull it equals Q over A, pull the area over here. Or this part would be the velocity. And then the area is, I didn't finish my equation here, R to the 2/3, S to the 1/2, A. And A is 112 feet. And that comes out to 130 CFS. I don't know if you're doing the calculations yourself. If you did them and I did something wrong, let me know. I could have made a button pushing mistake somewhere. So that was for 3 feet. Now we're going to go up to 6 feet. Another 3 feet. And this, as you'll see when we talk about stream morphology, there's also one of the quantities is there's to look at the width of the stream and the flow of the stream at 2 times the bankful depth. So this is 2 times the bankful stage or bankful depth. Just notice I got to write my 2/3 on there, and this 0 didn't show up there. All right, that should be right. So at 6 feet, the temptation would be to say, okay, I already have the number for the lower trapezoid. I just need to run the number for the upper trapezoid, but I don't think you're going to get the same number that way. So what we'll do is we'll write the equation, the whole Manning's equation for the whole thing put together. So for the geometry, for calculating the area, I calculate the area of this trapezoid plus the area of this, the top trapezoid. The wetted perimeter, I can take the wetted perimeter of this and then plus the wetted perimeter of this minus this length here, which is right about 40 feet. Again, the geometry isn't that complicated, but I won't spend time on it. And you ended up getting an area of 419 square feet, wetted perimeter of 110 feet, gives you an R of 3.8. And that's also has units, but again, we just plug it in there. And so if we run this, Q equals 1.49 for N R to the 2/3 S to the 1/2 times the area equals 1.49 over 0.03. That's what we used, right? 0.03. And our R is 3.8 to 2/3. Same slope, 0.00015 to 1/2 times the area, 419 feet squared. And again, this part of it here is the velocity. And we get a discharge at twice Banksville depth. We get a discharge of 2479 cubic feet per second. So the depth doubled, but the flow went up by a factor of like 20. And so when it gets out of its banks and spreads out on the floodplain, you get a whole lot more flow for not that much rise in the water. So that's the Manning equation, and that's the most straightforward way of doing it. I could, given Q, solve for depth. So given Q, slope, etc. Well, I wouldn't have area. I would have the slope and the Manning's N. And I guess I'd have to have the geometry. That'd be the way of saying it. I could solve for the depth, but that wouldn't be quite as straightforward, right? Because this A is a function of the depth and stuff like that. Given Q and the depth, solve for the slope. So I'm grading a site and I have some type of ditch or swale or something, and I have a flow I need to handle, and I have a depth I want to hold it to. What should I grade that slope at? Of course, you're bound a lot by the slopes on the site. So anyway, this is the most straightforward way of doing it, and in the exercise, the homework exercise, I just have you basically do a little problem with Manning's equation, and then the rest of it is dealing with the supercritical flow and subcritical flow, which is our next topic. So we'll pick that up.